Hello, my name is Aman Chaudhary.
My name is Mihir Sekhar.
And my name is Mhyank and we are all students at the Medical Science Academy at Hightower High School. My grandmother was unfortunate enough to be diagnosed with cancer twice. Aman's aunt also had cancer. In fact, when we look around among family and friends, far too many people have been affected by this dreaded disease. We decided to specify our project on a type of cancer called lymphoma, which is a cancer of the lymphatic system. The main reason for choosing lymphoma was that it is one of the most commonly missed cancers, which is truly devastating considering that with proper diagnosis and subsequent treatment, there is a survival rate of over 80%.
So we got together to try and figure out how to improve the diagnosis of lymphoma. As we are high school students, our medical experience is limited. Therefore, we interviewed lymphoma specialists at the hopes of better understanding the problems and barriers surrounding lymphoma detection. We learned that despite best efforts, lymphoma detection is ultimately dependent on human ability to analyze scans in a timely manner. While wondering on how to solve for this problem of human error, we remembered machine learning. What is machine learning? Well, machine learning is a program that improves automatically through its own past experiences. In today's world, machine learning is present everywhere, from predicting weather to recommending products to self-driving cars. So we wondered whether this could be adapted to our project and thus read scans. We hypothesized that a machine-based approach using artificial intelligence could pick up on subtle differences and allow physicians more time on complex cases. This would also allow physicians more time in analyzing and interpreting these results. This served our goal to incorporate machine learning into the process of detecting lymphoma. We aim to create a relationship between the software and the radiologist. This would also allow us to have the skills of the radiologist as well as the reliability and speed of the technology.
With a clear goal in mind, we then created a plan for how to accomplish our project. In order to succeed, we need to A. Obtain training data, B. Create the program, and C. Test it to ensure the software works properly and accurately. Our project did not require many materials. All we needed was an up-to-date computer that can run the software, CT scans from both healthy and lymphoma-diagnosed patients, and lastly, a software known as TensorFlow, but I'll get onto that later. For our project, we decided to focus on pulmonary lymphoma, which is lymphoma in the lungs, and we were able to get CT scans from over 150 different people.
To respect patient confidentiality, we obtained de-identified scans from the Cancer Imaging Archive and several published articles. We then analyzed each individual scan for pulmonary lymphoma using knowledge from the specialist we interviewed and online sources. Once the scans were correctly labeled, we could develop an algorithm for our machine learning program. We came up with a two-part program where the first component was to develop a visual detection software which analyzes CT scans and translates them into a format understood by computers. In the second component, we applied machine learning to study diagnosed scans and find attributes to correctly identify tumors. These two components complement each other to both learn the characteristics of lymphoma's appearance in CT scans and apply this learned knowledge in future scans.
For our algorithm, we used a base machine learning software known as TensorFlow. Although this is commercially available, we had to adapt it specifically for our project. For the actual program, we first had to create a model, which acts like a cheat sheet, using information gathered from hundreds of different CT scans with known results. Now, when the software sees a scan that it's never seen before, it looks back at the cheat sheet and finds common attributes, and then it flags this for review by the radiologist. All of this happens in just fractions of a second. The benefit of machine learning is that it's very flexible, meaning you can give it various different types of scans and it will still be able to correctly identify the tumor. Also, another benefit is that it's constantly adapting. It's constantly getting better and better with each additional scan, meaning 100 scans down the road, it will be exponentially better than it currently is. With the program completed, let's test it out. As you can see here, in this healthy scan, there are no highlights, meaning the software is 100% sure that this scan is tumor-free. In this next scan, we can see the software is quite confident in these two tumors and correctly highlights them for the radiologist. And in this last scan, we can see the program has no trouble easily identifying lots of tumors, even though they're in their early stages. This data table shows several random scans and how the program did with each of them. Overall, the program had an accuracy rate of 87%. At the start of our project, we created a success criteria to create a prototype that had at least an 80% accuracy rate when detecting tumors. Through our research, we found that 80% is a good margin to have because this shows that the program is working accurately and efficiently. And additional accuracy can be gained through longer testing times and more data.
Our software has a confidence rating, which increases its reliability. This gives the radiologist confidence in the program's capabilities. Considering that over 600,000 people are diagnosed with lymphoma every year, we see the true possibility of our project to save lives. Now with the base model fully created, we would like to expand our project to other forms of imaging studies, such as MRI scans, as well as PET scans. We would also like to expand our project to different forms of cancer.
Thank you for listening to our presentation. We have included an FAQ at the end of the PowerPoint for more information about our project.